Let's look at this limit, and we want to investigate it, determine if it exists or not, and if it does exist, we want to find the value of the limit. One thing you can do is to start by exploring some paths. So just because it may be the same on all paths doesn't mean it exists, but it may give you some idea what's going on. All right, so let's try along the x-axis. Right, in which case we have y equals 0. Right, and so now we're going to plug that in to our function, into our limit. Right, so if y equals 0, we now know that x is going to 0, and we have 5x 0 squared over x squared plus y squared. Oops, but we know y is 0, so let's replace that with 0 squared. So just simplifying here a bit. Well, the numerator is simply 0, isn't it? And the denominator is x squared. And since x is not equal to 0, we have 0 over some positive number, so the value of this limit is simply 0. You can get a similar thing on the y-axis. Those are good places to look in the beginning. So x equals 0. And if you plug in x equals 0 upstairs and downstairs, you'll simply end up with, I'm skipping a step or two here, the limit as y goes to 0 of 0 over y squared, which as above is 0. So maybe this limit exists and the limit is 0. Let's go back and look at the actual function we're taking the limit of here. So it's indeterminate. Both the numerator and the denominator are approaching 0 as x and y both approach 0. But notice, look at the degree of the numerator. It's kind of like a cubic function because it's got 1x and 2 y's multiplied together. So let's say that's a cubic. Downstairs we have something that's approaching 0 like a quadratic. Right? So if we looked at the line y equals x, say, we'd have 5x cubed on top and 2x squared on the bottom, and that would be 0. So it seems as if the value of this limit is 0. How can you actually show it? Well, there's a couple ways. One way is to use polar coordinates. When we have a limit at the origin in particular, and we can always shift the problem to have a limit at the origin. So we want here the limit as x and y both approach 0, 5xy squared over x squared plus y squared. The nice thing about polar coordinates is it kind of separates how far you are from the origin, that's r, from the approach to the origin, which is theta. Right? So if I substitute in here r and theta, right, r is going to go to 0 as x and y both go to 0, and we get 5 r cosine theta r sine theta squared over r squared cosine squared theta plus r squared sine squared theta. You might recognize that there's some nice simplification that happens there in the denominator. And why don't I have theta goes to 0 over here in the limit? Well, we don't really care what theta does. Right? What we're trying to show here is that r goes to 0, that when x and y goes to 0, that doesn't mean theta is going to 0. But we want to show that when r goes to 0, we get a limit that is 0 or maybe some other number, no matter what happens with theta. So let's simplify this. And I get 5r cubed cosine theta sine squared theta over simply r squared. Now notice, the value of the limit here has nothing to do with theta, so I'm going to factor that out. And even if it did, it doesn't matter because it's in the numerator here. We're never going to divide by 0 or anything. The limit as r goes to 0 of 5r squared, 5r cubed, excuse me, that's kind of hard to read because I wrote it so sloppily, over r squared. So I can reduce the powers of r there to simply 5r. And so we get cosine theta sine squared theta times 0 when we evaluate that final limit. Anything times 0 is 0. Right, so that proves that the value of this limit is 0. A second way to approach this is to use the squeeze theorem. Okay, since I think that this limit may be 0, right? If I can squeeze the function between 0 and something else, or between two functions which are both going to 0, all right, then that proves the function goes to 0 as x and y approach 0. So in this case, since we think it's going to 0, we can just worry about the absolute values. So if I go 0 less than or equal to 5xy squared over x squared plus y squared. Okay, the denominator is already positive there. Why did I put absolute values on there? That way I don't have to worry about a left and a right. Okay, if I can show that the expression inside the absolute value is going to 0, right, because it's less than or equal to something else, right? So what I'm going to do is stick an extra term in here, right? And that extra term is only going to make the denominator bigger. So less than or equal to 5x times y squared plus x squared. So I added x squared to the numerator. That only makes everything larger, over x squared plus y squared. Now we can cancel these. So this is less than or equal to 5 times the absolute value of x, right? And now as x and y both approach 0, right, 5 absolute x goes to 0. So we've squeezed the absolute value of our function between 0 and something approaching 0, as x and y both go to 0. So by the squeeze theorem, this guy has to go to 0 as well, right? So that proves, by this, let's write the words, by the squeeze theorem, that the limit as x and y, I'm just rewriting the problem, of 5xy squared over x squared plus y squared equals 0.